remember the Nobel Prize winner Richard Feynman, who wrote the book The Pleasure of Finding Things Out, which is banned in many communist countries. Anybody ever read these books? Anybody heard quantum electrodynamics? Richard Feynman? Okay, so that's what he got his Nobel Prize for. And in his physics talks at Caltech in physics, he's a pretty mathematical person, which is an important tool to have if you're doing physics or fluids or whatever. He says, what is the turbulence problem? And to start to talk, you got to say, the turbulence problem is not well defined. In fact, what is turbulence is even debated among turbulence researchers. And what is the turbulence problem is debated. Einstein says, the hardest part is defining the problem. So defining the problem is hard. We haven't defined it. Now, this is how Feynman would define a problem. And you all might be familiar with it. Let's say we have a pipe. And there could be water in the pipe. And the water goes in this end and out this end. And the speed of the flow in the pipe is slow, like the pipes in this building. And you might say, well, there's a pressure here. Call that P1. This is a P2. And we might say, if we set P1 and the water goes through the pipe at a certain inlet velocity U, what is P2? And you would have to find this result with just math, an analytical result, meaning by analytical, I mean a closed form equation for these variables. And you can't do that. Why? Because if the flow is slow, the flow is what we call laminar. But as the flow speeds up, it will go downstream and then it'll start to transition and become chaotic. And we call this transition to turbulence. Now, engineers would solve this problem with what we call Moody charts, which are just nothing but a bunch of experiments where they plotted the skin friction drag. And they could solve this problem today. So if you're an engineer, you could do experiments to find these quantities. If you have supercomputers, which were coming out really in the 50s and beyond to find flows for aerodynamics and nuclear weapons, then you would use a supercomputer. But there's no elegant or closed form mathematical theory that doesn't use empiricism. And by empiricism, I mean we're calibrating the method of experimental data. So this is how he would explain the turbulence problem. I'll show you the math community's view, which is more of Clay Mathematics Institute, looking at Navier-Stokes equations. But even if you solve this Clay Mathematics Institute problem for Navier-Stokes, it will still not answer this question. And it will be completely useless to people who have their feet on the ground, like me, who are trying to do practical prediction to do design. So that's the theme of the talk, is we are doing computations. It's not all my group does. I'll show you what my group does in 10 slides, just to get an idea of why we do CFD. And that's it. We are not smart enough to find solutions to the equations. But maybe one of you will one day, and you'll have my job. You'll have a Fields Medal, Nobel Prize, be a multimillionaire and work in any place, any government, any university in the world you want. So before we return to that, I'll also have to warn you that there's not a whole lot of math in the talk, because CFD as a field is 50 miles wide and 1 inch deep in English units. And you can choose any discretization method, numerical method, whatever you want to try and solve the equations. And I'm trying to show you what is the turbulence problem? What do we really care about today? What do governments fund? And what do we care about? What is the big problem? And what are the equations that government use, of course. So let's talk about my group. This is the slide I used to introduce it. I guess I got a pen. I'll stay over here on camera. I usually walk around. So here's two major photos I like to show. One is from Japan. It's a print. You can see that in the Met in New York. You can buy one of these for $50,000 today, or $1,000 if it's unoriginal on eBay. And it's also my group logo. And people in the turbulence and research community see that photo and say, you're a turbulence researcher. It's often used to say, this is a classic example of turbulence. The one in the middle is by Da Vinci. And since the antiquities, people have been studying fluid flow, mathematics, and fluid dynamics, starting with irrigation mostly. So my group is, number one, interested in the physics and math of turbulence. My life goal is to at least maybe understand turbulence and what it is, maybe the math behind it. And we specialize in wave science, and this is a central question. So here's a typical group. When I left NASA, this was my group, and you can see they're at a big tube. Anybody want to guess what the tube is? The exit of the big tube? Well, that is the exit of a hypersonic wind tunnel, which would move air at 7 times the speed of sound. And it's going to take a small power plant to run. And each experiment is going to cost minimum millions of dollars. And this is what we do experimentally in reality to study like Mars reentry or high-speed aerospace programs, weapon delivery, you name it. And so there's ethical questions in the field, but that's just the exit of the facility right at NASA Langley. And just a few fun things. Right now, I'm the DARPA Director Fellow. DARPA invented the internet, essentially. They invented stealth technology. They're the Defense Advanced Research Project Agency. If you read the newspapers, Russia and China are using hypersonic weapons, which operate faster than 5 times the speed of sound, up to maybe 20 or 30, to hit targets. And they have operational capability. The United States government is lagging behind, and I'm fully funded by DARPA to create analytical methods to predict flow fields around hypersonic vehicles. So this is how weapons in the future will be delivered. So I'm not here to talk about ethics. I'm just telling you what the facts are in realities. And you can take a stand either way, which is the great thing about a university. I'm just telling you what's happening. We also do computations of high-speed flows. That's just an example. I don't want to spend too much on this. We study high-speed transition. So if you look back at the cylinder problem, over here, the flow is nice and smooth. And at the end of the pipe, for example, it's fully turbulent. When flow goes from laminar flow, which is nice and smooth, to fully turbulent, it transitions. It becomes turbulent. This is a very, very, very difficult mathematical problem that people solve in instability theory. And people try and control those flows. Sonic boom prediction is another thing in our group. So we have taken measurements of the turbulent atmosphere, and we propagate the waves from supersonic vehicles to predict sonic boom. So NASA has a program called X-59 to demonstrate very, very quiet supersonic flights, so we can have supersonic aircraft in the future. And so there's mathematicians in NASA, computational people, wind tunnel people, all trying to understand the airflow around low boom supersonic aircraft. And then it's a math problem to solve the generalized Berger's equation, which is a nonlinear PDE from the aircraft to the ground to predict that sonic boom footprint. We've worked with teams to measure tornado formation. So we're solving equations of the atmosphere, Navier-Stokes, other ones, for chemistry, radiation, heat transfer from the sun, to understand how tornadoes are forming. And we do that with acoustic measurements. And we worked with tornado chasers from Texas Tech, which actually go out and take the measurements. So for a while, we had some undergrads, which were flying out to Texas for the summer. I was here working. They're out in the field, pulling up microphones, watching clouds. So what a great job for the summer. But you guys are mathematicians, so you should be doing math, not going around the fields of Texas, right? That's an engineer's job. We'll let them do that. Okay, now there's a new technique. If you look at finite element method, maybe of Galerkin formations, those do not work for CFD. They're often unstable numerically. They'll use things like discontinuous Galerkin methods with like upwinding, meaning we're taking differences in the opposite direction of the flow because of stability. And I had a Ph.D. student who graduated back from China, but he helped develop this with Stanford and NASA Glenn Research Center called spectral elements. So it's like a spectral differencing approach, putting numerical people in here. So it's ultra high order finite element method, just like you would have a spectral solver with like a Fourier transform, which is doing only finite elements. And this is running on the Chinese National Defense supercomputers to design gas turbines. And it's being highlighted in the supercomputing conference next month. I do aeroacoustics. That's what I did my PhD on. That's the study of like how acoustic waves come out of turbulence. And I don't want to go too much in this. I talked about transition. We want to control transition to turbulence. So we design control algorithms, which are just math algorithms, which drive plasma actuators to control turbulent flow. And you might want to do that on jet nozzles to do thrust vectoring or maneuvers without having moving surfaces. This is kind of stuff that's been used in the Israeli Air Force. Combustion, instability and noise. Originally, most rocket engines detonated or blew up due to what we call combustion instability. So in the combustion chamber, there's some sort of like resonance of acoustic waves, which we can predict with theory. That was developed originally in the Soviet Union, independently in the United States. And that's why most rocket engines blew up. So we studied how to suppress those with the US Air Force. This is just a picture of a CFD simulation of a flow field. And here you can see this is where the flames start during the machine. So that's just a broad, quick range. I don't really want to spend too much talking about my group and stuff. I came here to talk about a very specific topic, not analytical theory, not experiments, but this Navier-Stokes issue, which is my favorite set of equations ever. And there's even good YouTube videos, which are much more entertaining than me explaining what the Navier-Stokes equations are and how they're evaluated. But I hope that every graduate or undergraduate student in your department knows about this clay mathematics business, right? And getting a lot of yeses. So you probably read, was it how many unsolved ones? A few have been solved.
One solved.
One. What are you doing with your time? What are you guys doing Saturday night? I mean, so here's the one I care about. And I'm teaching Introduction to CFD. And the first homework set is to solve this problem. And they have 1 week to do it. Nobody's done it yet, but I say maybe one of you will do it. There's been cases like that where the professor's like, here's some unsolved problems. And then some student, super smart, comes back and so that was a really hard homework, but I did it. I said, oh, okay, so you're a genius and you can have my job. But here it is. This equation here is a divergence of a velocity field. And we call this the D'Alembert equation in the business because it was created by D'Alembert. And this equation is conservation of momentum. And I think I won't explain the notation. I normally would. Is it useful? Or I think most people in this audience probably know it. Okay, good. Yeah, it's nothing but, this is just a time derivative of velocity. This we call the convection term. It's nonlinear, unknown velocity, differencing in space. This term here is viscosity. This is your pressure gradient term, and this is your body force term. And if you look at this, you can almost interpret the problem on the board with these equations. The pressure gradient is basically P2 minus P1 divided by delta X. If you look at it from like a control volume side. And if you do one of these things, I guess you solve the problem. Big deal. You say the solution exists, it's smooth, well, it's incompressible, so whatever. See, the problem is there's no energy equation. You're not satisfying the first law of thermodynamics. And you said that the fluid is incompressible. There's no such thing as an incompressible fluid. So immediately the physics and engineering community says, this is good for some types of prediction, but it's not useful for anything I've shown you in the slides that we really care about. And the purpose of theory, when I worked at NASA for 7 years, the lead theoretician, Marv Goldstein, he said to me, Steve, the purpose of theory is prediction. The purpose of theory is prediction. So we did theory to make predictions to drive program. Land on the moon, go to Mars, launch satellites, design low boom aircraft. That's the purpose of the work. So this is a great problem. And I think we'll learn a lot mathematically, but I don't feel it helps people with feet on the ground do practical work for the benefit of society. And I'm an aerospace engineer, so we care about that. So here's a different set of equations. This is the Navier-Stokes equations, as we call them, not the incompressible form. This is conservation of mass. So rho is density, u is velocity. This is conservation of momentum. So you can see this time derivative term is a little bit different than the one in the problem, partial t, partial ui. It's a vector equation, 3 dimensions. You've got 3 equations. Here's your convective term. This is your pressure gradient. This is the Kronecker delta function. And this is your viscous stress tensor where viscosity is. Viscosity is not a constant. It depends on pressure and temperature and density. So you can't say it's a constant. If you do, you've made an assumption that ruins this problem. So you can't solve the turbulence problem if you're making some of these assumptions. Energy equation is the first law of thermodynamics, right? So E is energy, and you see Q is heat transfer. And these are just definitions of the different terms. So you really have three equations, but you have an extra unknown. You have density, pressure, temperature, and three velocity components. So you need another equation. What do you think that would be? We call it an equation of state or gas law. The simplest one you've probably seen is P equals rho RT. R is your gas constant, rho is your density, P is pressure, and T is temperature. That's the simplest one, but of course, in high-speed flow, where you might have plasma or reaction, chemistry, nuclear reactions, that equation won't work. But we also, I'll close simple problems with ideal gas law, that works really well. So now we have a set of PDE, highly nonlinear. There's just no, well, you know, it might never be a general solution. I never want to say never, but that's the pipe dream of my work with DARPA, is to kind of eliminate CFD runs for high-speed flow cases. But that's not what I'm here talking about. I'm talking about what we do today. So governments around the world and people around the world want to solve these equations. And you say, well, where do they come from? Where here's the history, because we're a university, we have to do history. I'm sorry, there's no poetry today. But here's Claude, Louis, Marie, Henry, Navier. It's French, 1785 to 1836. Anybody go to Paris before, the Eiffel Tower? No? Well, if you do one day, look at the Eiffel Tower. There's names on it, famous people. His name's on the Eiffel Tower. And I'm working with some French folks to find an oil painting. There's no known oil painting of him. So it's awfully nice. So there's just some fun facts. He was really a civil engineer who was very mathematical. Many of the best engineers had an excellent knowledge. Here's someone you should probably recognize, George Gabriel Stokes, Lucasian chair. And these two people, along with a number of others, took about 25 years to write down this set of equations. So it was a huge part of their life's work, and there's many more people. It's just that we name the equations after them. And you might say, well, why do they have their names and not other people who have done it, like Cauchy? Cauchy contributors too. Well, Navier was the one who kind of formalized it. It was invented in Paris by D'Alembert, and then Leonard Euler made corrections, and then Navier made the next big step. But there's this viscous term in the equations, and that was formulated by George Gabriel Stokes, which I'm sure you know from maybe when you teach Calculus 3 or something, which is a hard subject too. Yeah.
Do these changes come from like experiments, or like are you somehow able to visualize, make an idea of it?
Well, in this talk, I'm going to show you a number of experiments to show you what turbulence looks like. And I'll talk about how that's done if you want. And but these people were more mathematical. So up through the early 1900s, there was two groups of people. There were more like engineer types who just did experiments, and there's the math people. These are the math people, and they worked separately. They hardly talked to each other. And the bad thing is the math people said this will happen, and the experimentalists would say that's happening. And it turned out often they were both wrong. And only really in the 1900s did they come together. So I'm really a mixed person. I do experiments, I do CFD, I do theory, and you got to do all of them and understand all of them to make progress on the field. He worked on the problem because he was interested in the flow over spheres. Now, why do you think in his lifetime, the mid 1800s when he did this, would someone care about the flow, the fluid dynamic flow over a sphere? And that's why he has his name on the equations. Cannonballs is one good example. In fact, Isaac Newton and Eiffel, they were dropping cannonballs off of buildings to find drag and speed. But he was interested in pendulums. Now, pendulums are used primarily to what? Keep time. And in the British Empire, they were kind of colonizing the world and interfering in America's business, which annoyed me as an American. Sorry. And he was able to predict the drag analytically over a pendulum, which is really a sphere. And he corrected the time model of these clocks, which they put on ships. So if you're on a ship, you need two things. You need a pendulum clock, and you need a way to quantify where the stars are. And with those two things, you know you're exactly where you are on the planet. That's navigation fundamental 101. So you know the time and you know where the stars are. Then I know where my ships are traveling all over the world. I said flying because I'm in aerospace. They don't fly yet. Well, there are some flying ships, but anyway. So that's their story. Now, they weren't thinking about these equations as governing turbulence, but they do. This is Da Vinci's photo, which I already talked about. That's just a water jet in a fountain in Italy. And he draw all these little turbulent eddies. And when you look at it, there's tiny, tiny little scales and big scales. So this is what we call a multi-scale problem, that there's tiny little physics in the flow, and then there's big eddies. And there's a whole cascade or range from the little scales to the biggest scales. And that's all contained and should come onto the equations if we can evaluate them numerically. A few more historic photos. We'll have a little bit more math, but we want to get there about one of the most important theoretical studies of turbulence ever in the Soviet Union. This is a famous picture, and in it you'll see the Wright brothers, Charles Lindbergh, and this is at NASA, and this is sort of like pre-World War I type aircraft, post-World War I, 1934, and they had full-scale wind tunnels. They didn't have computers. This problem today is done with computers to calculate by numerically integrating the Navier-Stokes equations, energy equation, and gas law, the flow around the aircraft. So before digital computers came through with CFD, people would put a full-scale aircraft in a wind tunnel. We don't do that today because the wind tunnels would be even bigger. Because of computers, this wind tunnel has been demolished. And I was there when they knocked it down. There was a party. It was very fun. And that's where I got this picture. Now let's just look at the type of interesting flows that occurred. These are what we call Schlieren images. And this is of a projectile. That's what we call in the business, but it's basically a little bullet. And on the left, this is the bullet, the projectile, and it's moving to the left. And these are older pictures, but these types of pictures appeared in the 1800s. Einstein had a professor, and his name was Ernst Mach. Anybody heard of Mach? Then we call the Mach number after him. Mach number is the speed of the fluid divided by the local speed of sound. So these are traveling faster than the speed of sound, so m is greater than 1. And when that happens, you see all kinds of weird things in the flow, like shock waves, which are just continuous in the solution, and you see a turbulent wake. Now you could also look at a satellite picture of an island and see the same type of shedding or turbulent wake. So there's universalities in turbulent flows that are contained in those equations, and we want to find them. And we can scale flows from tiny little flows to big ones with these types of concepts. What you're really seeing here in the picture are the gradients of density. You're actually seeing an instantaneous picture of the partial derivative with respect to y, and y is what we call the cross-stream direction, which is in 90 degrees or orthogonal to the flow. So it doesn't matter if you're aircraft flying over the ocean, you'll have shock waves and turbulence over it. These are just other pictures of turbulence, and I could get into them. I mean, there's so many realizations. But what I want to tell you is that turbulence occurs at small scales within our lungs. It occurs in the atmosphere, around aircraft. When I walk across this room, there's turbulence on my skin, which is the boundary layer. It's behind me in the wake. When I breathe in and out, and the flow is turbulent. You just can't see it. Volcano eruptions are turbulent. They're jets. And there's astrophysics turbulence. So it happens all over nature. This is your basic airfoil problem. There's smoke going over it. This is where the smoke is going from left to right. And there's your airfoil. And if we raise the airfoil at an angle, increase the angle, then the flow separates and it's turbulent in here and it goes downstream. This is why when you put an aircraft at an angle of attack, increase the angle, it falls out of the air because it's stalling. Let's just look at a few others. Now, I only have so much time. This is the case where you can see laminar to transitional flow. And I've ruined all my undergraduate slides. I say on Saturday night, you're going to go in your kitchen and you're going to turn on your faucet. Just like this. This is not my picture. This is a poor undergrad picture of the phone. Anyway, they just turn on the faucet and this beautiful rod of water comes down. It's laminar. It's clear. And they call it laminar flow, these flow or streamlines of the flow, it's like a laminar desk. They're just perfectly aligned. And the water just goes over each other. laminar. Think of like a laminate dust. That's how I remember it. If I increase the water flow a little bit, all of a sudden it starts getting wiggles in it. That's transitioning to turbulence, just like in a pipe. Exact same type of instability in the flow. It's unstable. If I increase the water high enough, then this water jet will become turbulent. Also try this with like a hose or something. And this is the basic way you can see transition turbulence in your lives. Also unsolved problems. I never smoke, but I like watching people smoke because it's turbulent. And you might look at the ocean, flow over a submarine is turbulent right in there, in the river. And there's my last one, astrophysical turbulence. So in astrophysics, you might study that. And there's even some artists. Who's this artist? Thank you. I've got some art historians in here, not just mathematicians. And you might look at that as like a picture people used to say. So, okay, so we have the equations. We know turbulence is everywhere. We can hardly describe the turbulence problem, but this is probably one of the easiest and simple descriptions by a genius. And you say, well, I can do it experimentally, theoretically, or I can do it with computers, starting in the 50s when digital computers came out. Well, there's a famous fellow, Sir Horace Lamb, fellow Royal Society, and he had a quote, and he said, I'm an old man now, and when I die and go to heaven, there are two matters on which I hope for enlightenment. One is quantum electrodynamics, and the other is turbulent motions of fluids. It's a joke among physicists and failed engineers like myself, who couldn't be a mathematician, to say a quote like this. Heisenberg wrote his dissertation on turbulence, and he got out of the field because he felt he couldn't make progress in the field, and he went on and helped invent quantum mechanics. So there's really smart people working on this field, and they all have excellent math backgrounds. So you're in a position to attack the problem if you want. Now I say, okay, well, how do all these experts think about turbulence? And I just say, well, here's one of the most famous quotes. Turbulence is an irregular motion, which in general makes its appearance in fluids, gases, liquids. We should add plasmas. Plasma can be turbulent. And the flow past solid surfaces in the neighboring streams of fast flow, blah, 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 blah. And, that doesn't mean a whole lot. So people took that and made even better definitions. And these are all different people's definitions of what turbulence is. So you see, even the experts in the community over hundreds of years couldn't even define the problem and say really what turbulent flow is. But I think we have a physical idea of what it is. Like we know it when we see it. But defining it mathematically is very hard. Okay, now we're going to do the most important statistical theory in turbulence. I'm just going to show you the results. And I'm sure you've all heard of Prof, mathematicians Soviet Union. Now, imagine it's World War II. You're in Moscow. You have no water, you have no electricity, and Stalin knows your name. You're not leaving. And your office is in a bathroom. You're Andrei Komarov. What are you going to do with your life? You're going to think about turbulence theory. That is truly remarkable. And this is the outcome of this theory. And you can download the paper. And if you don't have it, I have it in Russian and English. Just send me an email. I'll email it to you. It's the most celebrated statistical theory of turbulence. He took the Navier-Stokes equations and he did a bit of a rearrangement and he did a statistical analysis for what we call high Reynolds number, high intensity turbulence. And this is the problem we talk about today. Let's say we have a little box in the atmosphere. And the length of the box is something like L. And the biggest turbulent eddies in the box are maybe about L. And then there's tiny, tiny little turbulence in there. And that length is, we'll call it eta. Eta. So if you think in this room, if we all wave our hands around a lot, then, well, even now, the whole room is full of turbulence. It's amazing. Just because of the convective motion of the HVAC system. You don't see it, but this whole room is full of turbulence. And in this room, there's a turbulent eddy, which is about maybe 1/3 the length of the room right now. We can't see it. Well, I could fill it with smoke, but then I get in a lot of trouble, right? I don't want to lose my job yet, or for a better reason than that. But then you say, okay, if I know or can estimate the biggest scale of turbulence, what is the smallest scale? Only from knowing the biggest scale. If I know L, can I estimate what the smallest scale of turbulence, which is the smallest little scale of turbulence, a little eddy. And he did that. And that's the outcome of this theory. that there's a universal cascade or universal theory of turbulence. And this is the result. This value is the size of the smallest eddy of turbulence, eta. This value is the viscosity, which would be relatively constant. In this room, that's about 1.5 times 10 to the negative fifth. And then there's this value called epsilon. And epsilon is the rate of decay of the energy. So you can calculate energy. It's about 1/2 times the density times the velocity squared. If that energy, 1/2 rho v squared, decays, it actually decays at roughly constant rate. I take that value, here, K is the kinetic energy and its rate of decrease with time. I plug it in there and I can estimate the smallest scale of turbulence. Now let's think about this for a real problem. And we take measurements and we confirmed his theory. It works on the sun, it works in the atmosphere, it works in my lungs, which are in turbulent motion, and it's very accurate. Let's say I'm in the turbulent atmosphere. What's the largest scale of motion in the turbulent atmosphere? If I look at a satellite, I can see a large scale, it's like a hurricane. If I'm away from a hurricane, I still have scales which might be multiple kilometers. Then you say, okay, my biggest eddy, my biggest rotating structure in the atmosphere is a few kilometers. Just using his simple theory, the smallest scale will be like the thickness of my hair. So you can see the scales of turbulence might be like 10 to the negative 4th or 5th meters, all the way up to kilometers. On the sun, the largest scales are bigger than the Earth. And the bigger the larger scales and the higher the rate of dissipation, typically the smaller scales of turbulence. This is just how you estimate the time and velocity scales of the small scales. So now you've learned the most important theory, or the outcome of it, not how it's derived, of turbulence. And some people say nothing in turbulence theory has been done since 1940s in Andrei Kolmogorov's bathroom office. So I think to myself, here I'm at a university. I have all the technology. I have a bathroom. I have electricity. I have computers. He didn't have computers. What's my excuse for not understanding turbulence? Anyway, I guess I'm rather privileged. Now you say, well, what does this have to do with computers? Well, it turns out that you can relate the smallest scale eddy, the largest scale divided by the smallest scale. So that's the big L divided by the tiny little eta. And through some just dimensional analysis, he showed that it goes as the Reynolds number to the 3/4. So Reynolds number is named after Osborne Reynolds. That's the density times the velocity times the length divided by, Reynolds number will be the velocity of the flow divided by that big length scale divided by viscosity. So that's Reynolds number. And if we raise that to the 3/4, then that will be the ratio of L over eta. Now, for high speed flow, Reynolds number gets big. Why? Because U is velocity, and it's going to get very big. Now, if you have a very, very low speed flow, it turns out to be laminar. We don't care about that. We care about high Reynolds number, high speed flow. And high speed flow, in the context of this problem, might only be a meter per second, which is very slow. And that brings us to CFD. The turbulence problem from this context drives why we do CFD. I know I got only a few minutes left. This is just what CFD is. It's basically anytime you numerically solve any equation that models fluids, you're doing computational fluid dynamics. In this case, we're looking at CFD. It was originally done by teams of human computers. So at NASA, they would have, you had to be a woman to be a computer, and that was your title, and you had to have a math degree. Oh. Yep. And so if you saw the movie Hidden Figures, this is the woman who starred in it. I mean, that was actually her. Okay. And that was a sought after job. And in the 50s, people like von Neumann and others, with Einstein at the Advanced Institute, there's Neumann, Einstein, drove computer technology to simulate nuclear weapons and high-speed aerodynamics. We'll skip that slide. Now let's say I discretize the Navier-Stokes equations and I integrate them in time. How much computer power will I need to resolve and simulate a flow? And in interest of time, this is just the analysis of how it's done. I wanted to show you the result. But basically, I'm kind of estimating the number of grid points, the delta x, and the time step delta t when I discretize in space and time. And I estimate how much computer cost that will be. And turns out it goes as 9.2 times that Reynolds number to the 3/2 power. So here's the result. Let's say my Reynolds number, which I just introduced, that's rho times U times L over dynamic viscosity, is about 94. That means I need about 1.1 times 10 to the 6 cubed grid points, 1 million grid points in 3 directions on your computer. Has anybody solved a million by a million by a million problem on their computer lately? I haven't, but that'll take 20 minutes on a computer, which is about 10 years old. Now, if my Reynolds number is just under 100,000 on a single processor over a Reynolds number with 7.8 times 10 to the 11 grid points in each direction, to resolve this will take me 5,000 years. 5,000 years. Now, what is the Reynolds number of an aircraft we flew on? It's huge. It's tens of millions. So we can only resolve about 100,000 when we need a Reynolds number of tens of millions. And this is not scaling linearly, obviously. So if you look at a DNS, a simulation, just of discretizing an airflow of an airplane, which isn't even that fast, you would have to take all the computer power we've ever had over the entire history of humanity to simulate it. And you still wouldn't have enough computer power. So we hope that something like quantum mechanics and magic will come along to give us the power. So then we say, well, there's turbulence modeling, which is a whole other story. But this is the limitation of computers. And we have to use a lot of tricks to model the turbulence instead of actually integrate it. I know I'm running out of time. I apologize. Let me just show one more case. It's very much like this pipe problem. So flow goes in here and it comes out here. And what they do is they put a little backward facing step here so the flow comes in and it kind of circulates around and goes downstream again. This is a classic problem experimental study to understand the physics of flow. It's called the backward facing step problem. There's a classic Cray machine. To solve this tiny little problem, took 54 days on the Cray and fully loaded. So this is where the supercomputer time is going. 70% of NASA supercomputing time is used on CFD. 70%. You think, oh, it's astrophysics or something. No. It's all CFD on reentry vehicles. Like, I want to put a person on Mars. There's no way to do an experiment because we haven't done it. Think about the first time we put something on Mars. We never had a measurement of the atmosphere. We don't even know what its composition is. So we were doing CFD, which is the only way to study it. And I think I've just given you a taste of the problem, but let me show you a case study I was involved in, just as the last few minutes. So NASA's building like a space shuttle replacement. You might say it's good or bad, but they are. And it's called the Space Launch System. It was named by politicians. The NASA researchers called it the Senate Launch System because it's funny. It's designed by the US Senate. Anyway, I went across the street and there's this model in the wind tunnel. That's the model of the vehicle. So they started doing experimental tests to study the airflow at high speed and also the airflow across the launch pad. And this is what sort of modern CFD looks like. Grids and results. They're going to do CFD with combustion through the rocket nozzles. They're going to have an abort system with grids. Here it is on the launch pad. This CFD was done at NASA Ames. So there it is on the launch pad. There's a crosswind going this way. This is the rocket plume as it rises and it goes through trenches. And a good question is like, well, why would we use NASA Ames supercomputing to eat up the machines? I mean, we're talking a lot of money and time and people to study the problem. Well, when rockets take off, there's a crosswind and they drift. Sometimes they're actually pushed into the launch tower, or sometimes they're pushed the other way and the rocket plume actually misses the trench. So if you go to NASA Kennedy, you can go out to those old launch pads and see the rocket trenches. If it misses the trench, the rocket exhaust comes down and hits the ground and it bounces back and it could destroy the vehicle and it damages the launch pad. So these are the types of simulations you might see. And I just scroll down and you can take a second to appreciate different types of CFD that's being run today. This is a jet and cross flow. This is a wind turbine. This is just turbulence itself. I talked about the smallest eddies. Well, these are little hairpin vortices, the tiniest little eddies. Convection, if you're cooking, you can look at the water in your pan and see this type of convection cells. This is just visualizing boundary layer turbulence that might go over the skin of an aircraft. Pollen, rain, and wind. Vorticity, this is a simple problem you might study in math, incompressible flow. Atmospheric turbulence. Liquid jets, talked about the liquid jet. This is fully resolved DNS, and the Reynolds number is only 1600. So you can do that. Large eddy simulations, a technique to get away from the computational limit of DNS, direct impulse simulation. Now that's really the end of my talk. I hope you just see like a big appreciation from where we started from agricultural in Babylon and Sumer, which is really the first civilization of my understanding, in Iraq, all the way today, where we're in aerospace moving hypersonic vehicles to deploy nuclear weapons. So thank you. That's it.
Any questions, Dr. Moore? I think it's like,
How's the pizza?
delicious.
There you, that's all I needed to know. It's worth it though. I got pizza to hear me drone on about integrating equations. But you know, this talk is like very straightforward. We say, okay, here's the problem. This problem can't be solved. So if you take those Navier-Stokes equations and tell me the drag given two pressures, then a lot of people will say you've solved it. You understand it. Nobody can do that. So simple. Maybe.
I have just a general question. I know like multi-scale problems are really challenging. So I'm curious what some of the go-to tricks are that you use when you're actually trying to solve them.
Yeah, so that's something I haven't talked about. So Reynolds might say there's really two major methods. You take the in CFD. In the Navier-Stokes equations, you can say, say I have U, that's the velocity. And for every variable, you just say U equals U bar plus U prime. U bar is like a time average variable, and the prime is the fluctuating variable. So you can take any variable and decompose it into its average and a fluctuation value. That's called Reynolds averaging in the business. And I take that averaging quantity and I put it in the Navier-Stokes equations. And I simplify them. Now, I am now trying to solve more equations because I've taken every unknown and made it into two unknowns. And you think that is a stupid idea because I only have so many equations. Well, the idea is I will take statistics of the average values and the fluctuation values, and I actually reduce the number. And then I create new equations to model turbulence. So turbulence modeling is the predominant way that people solve fluid dynamic problems today. It's called turbulence modeling. I teach a whole class on it next semester where we go from the very beginning of CFD and develop turbulence models. We even create a basic CFD code with a basic turbulence model for incompressible boundary layers. And that's all of MAE, the mechanical and space department. So the idea is like, I'm gonna not predict the actual fluctuations of turbulence. I'm gonna predict the statistics. Now there's another big advantage for that. The experimental people, they can really only measure statistical quantities. So why should I care about predicting actual fluctuations when nobody even really cares about them in practice? We want to find the average values of the flow. We want to find the statistics of the flow because it's really a statistical problem. Turbulence is a statistical problem and a continuum problem. So that's one technique. The other technique I said is like the computational power is driven by the largest scale and the energy dissipation rate. And the smallest scale turbulence we need to resolve with grid points. Now, what if I could not worry about the smallest scale? What if I say, okay, the smallest scale is now 1,000 times bigger. So I'll use the computer to just simulate the big scales, and I will model with new equations that I create what happens to the small scales. And you say, well, that's crazy. But there's a universal behavior of turbulence at small scale. And I know what that is from theory. So I take, yeah, like Kolmogorov theory, and there's newer ones too. And we call that subgrid scale modeling. So you have a computational grid, and you say, well, I have Nyquist criteria. I don't know what's going on between the grid points. I model that with mathematical theory, which has been validated with computers.
Like the coarse grid is some sort of initial condition for the boundary.
Yeah, so we have a coarser grid. So we're filtering out the small scales and we're modeling it. So we solve more equations, but we have way less grid points. And then we can create flows that look like this. So that's really what you're seeing. You're seeing turbulence modeling. You're seeing in one of two major approaches, which is the grids filtering or averaging and finding statistics. So that's a great question.
But I know we're over time, so if you don't
Yeah.
really, feel free to, but I don't know if you have time.
Yeah, I'm here. It's cool. If anyone wants to talk after, thanks for coming. And you're in one of the best departments on campus, aerospace and math, best departments. So keep doing the great things you're doing. There's no part of math which is not useful. And you're just the stars of the academic world. So it's my honor to come to math and learn from you.
Yeah, thanks for coming.
Yeah, thank you. Thank you.